Okay, if you have not already done so, you should grab out your notes packet, grab a calculator. Today's lesson is fairly straightforward. We are on page, I believe it's 7 of our notes packet. Yep, page 7. So we're still focusing in on that Pythagorean theorem. Now, Pythagorean theorem, the regular theorem, is used to solve for a missing side length, specifically in a right triangle. But we also have Pythagorean inequalities as well as the converse of the Pythagorean theorem that we can use. Now, converse, remember, is the reversed version of the if-then statement. So Pythagorean theorem itself stated if we have a right triangle, then, well, there's more to it, but we could do a squared plus b squared equals c squared, where c is the hypotenuse length. The converse allows us to say if a squared plus b squared is equal to c squared, then we can determine that it is a right triangle. But we can not only determine if it's a right triangle, if it's not equal, we can determine if it's an obtuse or an acute triangle. Specifically, if the a squared plus b squared is bigger than the c squared, so that c squared piece is the smallest piece, it ends up being an acute triangle. If it is equal, it's a right triangle. And if the c squared piece is the larger of the pieces, it is an obtuse triangle. So you're going to see problems that ask you if the triangle can be acute, obtuse, or right. Now, do pay attention to the instructions, because sometimes it might also ask you if the following could create a triangle at all. Now, this one doesn't. This one says they do make a triangle. If it asked if they can create a triangle, that's when you're doing what we did yesterday, which was that determining whether it's possible using the triangle inequality theorem. So, this one says it can make a triangle. We want to classify it as acute, obtuse, or right. So, first thing you have to do is determine which side is the largest, because that side, if it is a right triangle, is going to be the hypotenuse. 6, 4, and 3. 6 is definitely the biggest. Which means when I do my Pythagorean theorem, that's going to go in C. The other two are going to be A and B. Doesn't matter which one's A and which one's B. The difference compared to yesterday, though, is when I do my a squared plus b squared, which I'm going to choose to do the 3 first, I don't know if it's equal to c squared because now I know what c is. So I'm going to put, similar to yesterday, a big open box that just talks about the relationship. 3 squared is 9. 4. Why did I put a 3 in that exponent? Don't do that. Oh my goodness, Benson. Get it together. It's a squared. Anyway, 4 squared is 16. And 6 squared is 36. And I still don't know the relationship. So I just kind of leave myself a big open spot. 9 plus 16 is 25. And compared to 36, 25 is less than. It's smaller than. So, since in this case, this was larger, when the c squared is larger, that's when you get a or an obtuse triangle. Okay, let's try another one. My side lengths are 4.3, 6.1, and 5.2. 6.1 is clearly the biggest. So that when I do my converse of my Pythagorean theorem and my Pythagorean inequalities, that goes in for C. Doesn't matter which one's A, which one's B. I'm just going to go in order. 4.3 squared plus 5.2 squared, big open box, 6.1 squared. 4.3 squared is 18.49. 5.2 squared is 27.04. Big open box, followed by 6.1 squared, which is 37.21. I'm going to combine my like terms, which is the 18.49 and the 27.01, and I get 45.53, which compared to 37.21, 45.53 is bigger. So this is my C squared piece. I always focus in on it. If it is smaller, then that means we're fitting the first of the three pieces of the theorem, and it is an acute triangle. C squared smaller, acute. C squared bigger, obtuse. C squared equal, right. Now, some of the problems are going to look like C, where you got side lengths of 6, 4, and square root of 13, and it's less obvious to tell which of these is biggest, because while some of us might be like, well, 13 is clearly bigger, it's not 13, it's the square root of 13, and the square root of 13 asks what number multiplies by itself to get 13, which is not an obvious number. But you've got a calculator. So, you open up your calculator. You type in square root 13 equals. And it tells you that the square root of 13 is 3.605512755, etc. Now, if this is about 3.6, that means the biggest side is the 6. Now, you have to be careful. You look at the decimal in the calculator for one reason and one reason only: to determine which side is bigger. When we choose to do our a squared plus b squared equals c squared, where c is equal to this, and I shouldn't have said equal, I don't know if it's equal, I do not plug in 3.6. I must plug in the square root of 13 into my Pythagorean inequalities. So 4 squared plus square root of 13 squared is something compared to 6 squared. I cannot put in the decimal unless I want to open myself up for the possibility of a wrong answer. 4 squared is 16. Plus square root of 13 squared is 13 because the square and the square root cancel. 6 squared is 36. 16 plus 13 is 29. 29 compared to 36. 29 is definitely smaller, which means 36 is definitely larger. And if c squared is larger, then it is an obtuse triangle. Now, final problem. Looks awfully darn ugly, and I know it looks ugly, but the process is the same. Start by finding the biggest side. I've got square root of 2, square root of 5, and 3 square roots of 4. Now, if it was just square root of 2, square root of 5, and if this 3 weren't here, don't scribble it off. I'm just doing this to show you something. If that wasn't there, the biggest one is going to be the square root of 5. But that 3 throws things for a loop. So that means I'm going back to my calculator. Now, between the square root of 2 and the square root of 5, the square root of 5 is bigger because it's got a bigger number inside. So I really just have to compare the square root of 5 with 3 square roots of 4 to see which of those is bigger. Square root 5, 3 square root 4. Well, 3 square root of 4 is 6, which is definitely bigger than 2.23, etc. So, that's the biggest side, which means that is what goes in for C. Square root of 2 squared plus square root of 5 squared has some relationship to 3 square roots of 4 squared. Now, remember, we talked about this yesterday. When the entire side length includes both a number in front of a square root, you need to put parentheses. Now, in all actuality, the square root of 4 is a nice perfect square. Not to mention, we already put 3 square roots of 4 in our calculator, and we found it was 6. But for the sake of argument, we're going to say, hey, let's say we don't know what it is. Let's say it's not a nice number. We put it in parentheses like this. Square root of 2 squared is an easy one. Squares and square roots canceled, provided there's not another number in front that's messing with it. Squares and square roots still cancel. That's 5. 3 square roots of 4 squared. Go to my calculator. I open up a set of parentheses. I do 3. Then I do square root. Then I do 4. Now this calculator looks a little different than the baby TI calculators because if you notice, everything I'm typing right now, it's just making the square root longer. And some calculators do that, and if you have that, it becomes less of an issue. You got to hit the right arrow to get out of the square root. If you're using the little baby TI calculators, it's going to put a parenthesis right here. So you got to make sure when you get over here, you close both of those parentheses. And my calculator's yelling at me because of where I put the parenthesis. There we go. Let me try that again. Anyway, open parenthesis, 3 square root, what goes inside. Either get out of the parenthesis or close the parenthesis, and then make sure you're closing the outside parenthesis before you're squaring it. And we get 36. Seven is definitely smaller than 36, and since the 36 is the larger one, it is an obtuse triangle. Now, the only example that you did not see is a situation where the two sides end up equal. I must have accidentally changed a problem that got rid of that. That was 100% a mistake. But if the two sides are equal, then it's a right triangle. Now, the other thing you're going to see today kind of goes a little bit different, but it's also a fairly easy concept, is this idea of what's known as a geometric mean. Now, geometric mean will bring us a little bit back to Chapter 8 in the fact that it makes us create a proportion. A geometric mean, by definition, is a positive number x that satisfies a over x equals b or equals x over b. If you want to find the geometric mean of a number, this formula here is just giving you a structure of where to put your numbers. You're solving for x, and a and b are the two numbers it gives you. Doesn't matter which one's a, doesn't matter which one's b. I like to call the first one a, I like to call the second one b. And we're solving the equation 98 over x equals x over 18. We have a proportion. We cross multiply to solve. I do 98 times 18. I get 1,764 equal to. Now, x times x, when you're multiplying variables, you add their exponents. If you can't see an exponent, it's an invisible little tiny 1. And 1 plus 1 is 2, so it's x to the power of 2. And it's always going to be x squared when it's x times x. To get rid of a squared, we take the square root. Now, when you take square root, what typically goes with it again? I hope you said plus or minus. I hope. So x equals. But here's the thing. Geometric means also are never negative. It's just $42. At least for our purposes, they're never negative. So you don't have to worry about the plus or minus, but it's something to keep in mind. Okay, problem B, same thing. Looking for the geometric mean between two numbers. You set up the proportion. The x's are always x's. The two numbers go in the A and the B slot, doesn't matter which one's where. And you cross multiply. 24 times 48 is 1152. X times x is x squared. I square root to solve. Rounding to the nearest, rounding to the nearest hundredth. Be careful of your rounding. I get 33.94. Sometimes the numbers that you're looking for the geometric means of are not pretty. Like C and D have some ugly numbers. And that's okay. When you have ugly numbers, it doesn't change your process. X goes there. X goes there. 12 squared 2 goes here. 27 goes here. Now the x times the x, that's the easy part. That's x squared. On the other side, I've got the 27 getting multiplied by the 12 and the square root of 2. Now we can multiply that together and simplify it, or we can leave it as is. Do which makes the most sense to you. Now, if you're going to multiply it, when you're multiplying a whole number by a square root, the whole number gets multiplied by the whole number, and any square roots get multiplied by any square roots. There's only one square root in this problem, which means when I multiply it, I'm multiplying 27 times 12, and the square root of 2 is just going to stay a square root of 2. To get rid of the squared, I take the square root, and that square root needs to be over this entire thing. So, what that means is if I've got one of the fancier ones, I'm looking for the square root of 324 square root 2. And I need the big square root to go all the way over this square root of 2. Now, that's on this fancier TI, which, by the way, I get 21.41 when rounding. If you don't have the fancier TI, which, let's be honest, I don't expect that you have the fancier one. You don't have to have the fancier one. To put the square root of 324 square root 2 into a calculator, if you've got one of the others, it's going to look like this. Square root. Square root symbol. Your calculator is going to give you an open parenthesis if you've got a TI. If you have a Casio, you need to put that parenthesis in. Then you're going to do 324 square root symbol. Your TIs are going to put a parenthesis there. If your Casio doesn't, put it there. Then put a 2, then close, and close again. Now, that's if you put in the version that was simplified. I also mentioned you didn't necessarily have to multiply the 27 times the 12 square roots of 2. So that's if you did it this way. If you did it this way, and I should have maybe put these in the other placement, you can take the square root of 27 times 12, square root of 2. It's going to look like this on paper, which, if you have the fancier one, and I'm going to bring that back up, on the fancier one, it also looks like this, which is the exact same thing as what we got before. Or, if you've got the not so fancy TI, on a calculator, that will look like square root, parenthesis, 27 times 12, square root, parenthesis, 2, close, close. So for the most part, you type them into the calculator very similarly. The difference is, are you going to have that 324, or are you going to have 27 times 12? Last problem, similar in idea. Fraction, fraction, x here, x here. My numbers are 3 square root of 5 and 8 square root of 20. X times x is the easy part. That's x squared. 3 square root of 5 is getting multiplied by 8 square root of 20. Now, I do typically multiply them, but again, just like before, you don't have to multiply that out. You can leave it like that, and I'll show you what it looks like in a calculator. But if you do multiply it out, whole numbers with whole numbers, square roots with square roots, you're going to get 24, and that's going to be the square root of 100, which in itself would be a nice number, and you could simplify that and we could keep going, or you can leave it like this. More commonly, it's going to be left like this. To get rid of a squared, we take the square root, which that square root goes over the entire thing. So in my fancy calculator, what's on the right side is going to be what I type in. 24 square root of 100 inside of a square root. Oops, wrong button. $15.49. Which I don't need the plus or minus. If I did not actually multiply this out, and I go to take the square root, it's going to look like square root, parenthesis, 3, square root, parenthesis, 5, close 1 parenthesis, times 8, square root, open parenthesis, 20, close 2 parentheses. Either way, it should get you 15.49. It's not the ugliest thing or prettiest thing in the world. That being said, we're not going to see a whole lot with geometric means in this chapter. So it's kind of a little offshoot thing. It's fairly easy to do. It's a lot of calculator work. Yes, you do need to show your work. Showing your work means you need to, at very minimum, write, for example, your inequality. But otherwise, that is it for today. Reminder, 9.0 worksheet is due today. Today was 9.1, day 2. It is the 27th. Since it is Thursday, our homework is going to be due on Monday, which is the 31st, but we should not delay till Monday because tomorrow you have a quiz. Be amazing for the sub. I will see you all hopefully tomorrow, possibly next week. We'll see what things look like.